Hello, and welcome to this installment of Physics in a Flash. We're going to give an overview of the first unit of study in AP Physics 1, kinematics. If we were to look to define what kinematics is, it's identified as a subfield of physics. It describes the motion of points, bodies or objects, and systems of bodies or groups of objects, without considering the forces that cause them to move. It's descriptive. It doesn't explain why. So we say that kinematics deals with what the nature of the motion is, other subfields get into explaining why. That's reserved for other subfields. So typically, kinematics begins with describing the geometry of a system, then declaring initial conditions, and those initial conditions would relate to position, velocity, or acceleration. Then we use arguments from geometry and the position, velocity, and acceleration. They can be determined from unknown parts of the system. And a key word here that's omitted from the official definition is prediction. We can predict the future movements based on current conditions. So in AP Physics 1, we might first ask what types of motion we'll study. And what I would like you to think about as we go through this course is to ask ourselves always, when there's motion involved, is the acceleration constant or is the acceleration changing? It turns out that's extremely important for us to know. When we have constant acceleration, we can have constant velocity or changing velocity. So changing velocity can be due to either constant acceleration or changing acceleration. But constant velocity can only be due to constant acceleration. But notice the important thing is to determine first what's happening with the acceleration. How we ascertain the velocity and what's happening with the velocity is a study of the position of the body, how that position is changing over time. That is position versus time. That allows us to determine what happens with the velocity and therefore the acceleration. Now, when it comes to looking at the motion of position, there are three types of motion we would experience. We would experience or study linear motion, circular motion, and oscillatory motion. And I already referred to those in the introduction to AP Physics 1 in the first installment. So that they're either motion in a line or in a circle, or it could be oscillatory, back and forth, and back and forth, and back and forth. And circular motion, traveling in a circle of some type, and linear motion, traveling along in one dimension. In our journey, I recommend that you watch the movie Flatland, the movie, to help visualize what we're talking about by linear motion. And in linear motion, you would pay special attention to the place they travel to, which is called Lineland. In Flatland, the movie, which I've shared the links for in the video. So when we're talking about kinematics, these are all the concepts involved. And I like to break them down into two types of concepts. Those that are definitions and those that are relationships. The definitions consist of mathematical expressions or mathematical definitions. So in this case, we have V, which we see stands for velocity or speed. So if it is speed, the line over the top means average. So the average speed is always, always, always the total distance divided by the total time. In some conditions, it is also equal to the instantaneous velocity plus the initial velocity over 2. Now notice for velocity, for velocity or speed in these cases, I used and referred to three different adjectives. Initial and average are pretty straightforward in terms of what they mean. There can be a little bit of confusion about what a variable means. For example, this V, or this V and this A, when there is no subscript. we see the subscript here, v0, meaning initial speed or initial velocity. And that's the one that we see most oftentimes. But we do sometimes see we also see the average sign over the top. And none, when there is none, that means either we're referring to the instantaneous, that value at any particular moment in time, say the initial conditions, or the final condition, or some condition in between. So we can imagine a particle moving like this, and we could say this occurs at time 0, and this is an instantaneous time 1, position at time 1, position at time 2, position at time 3. Now, if we are focused on these two portions of the motion, then this is clearly the initial, and this is clearly the final, even though the object may have continued to move on afterward. Final is defined by that period of time we are investigating. So it's not an absolute. It's not when the whole thing is done moving. It's over the interval we're looking for. So similarly then, we may move on and want to study a little bit further in that motion, and we say now, okay, we want to look at this interval of time. Well, now, this is the initial, and this is the final, or instantaneous. So it comes back to exactly what we mean. So interpreting a formula such as this one up here, this says the instantaneous velocity is equal to the instantaneous acceleration multiplied by the time plus the initial velocity. And since the time is a variable, it kind of suggests that we are looking at motion over a period of time, and we are only looking for the velocity at one instant. Now, it may happen to be, it's at that instant that it happens to stop its motion. So, we have our definitions. And our definitions, and all of the quantities we experience have adjectives. So, every quantity, acceleration, distance, jerk, velocity, time, and position, can have any one of these three adjectives ascribed to it. Instantaneous acceleration, average acceleration, instantaneous acceleration, and so on. Which leads us to another problem that students sometimes have with this word quantity. A quantity is any attribute that can be measured. It does not mean a number. It does not mean a number. The quantity of things is not 6. The quantity of the distance is not 6. The magnitude of the distance is 6. So when we are talking about a number, that is reserved the number of magnitude. So let's take, for example, the quantity height. What is the magnitude of the height? Oh, the magnitude we might say is 2.64 meters. That is the magnitude. The quantity is the height. It's the thing being measured. So we have quantities, adjectives, and those can all be applied to the formulas that are our definitions. So our first definition, as we started, was the average speed or average velocity, total distance over total time. Under some conditions, it is also equal to the instantaneous velocity plus the initial velocity over 2. The definition here of displacement is the change in position, the average velocity. You'll notice for each one of these formulas is going to have its own video to go into depth, but you'll notice these two look an awful lot like each other. And then we have this, and we have these. So these items highlighted in yellow require constant acceleration. So if the acceleration is not constant, we can't use those formulas. Our relationships one thing that typifies relationships is they are graphical. You should picture a value of something against time, either position or velocity or acceleration versus time. And the third formula category is what I call they're neither definitions nor are they relationships. So one of the formulas that you will see quite often if you're looking for sources on the internet is you might see a formula that looks like this. I will never use that formula because it is the combination of these two formulas. Solve for t and then put that in here and you get this. So one doesn't ever need to use this combined formula. The next bit of terminology I want to introduce you to is the idea of fundamental units or fundamental quantities. Fundamental quantities refer to those 7 SI quantities that we've already learned about. That's it. So those are measured in meters and amperes and so forth. So those are the 7 SI quantities. Now derived units or derived quantities are those that are the result of combining fundamental quantities. For example, velocity is not a fundamental quantity. It is a derived quantity because it is built off of fundamental measurements. So we might have units of meters per second. These would be derived units. And velocity itself would be a derived quantity. We also have, sometimes we have situations where there's a formula like this. F equals ma. And the units are kilogram meters per second squared. Now, since we see that we can measure mass, that's a fundamental quantity, and distance, that's a fundamental quantity, and time, that's a fundamental quantity, using all of those fundamental quantities together, we can come up with a new quantity. And we could say force has units of kilogram meters per second squared, but that's a mouthful. So sometimes we do a new kind of substitution, and we will define that as 1 Newton. So whenever we have 1 kilogram meter per second squared, that's equal to 1 Newton, and we would say the force is then 10 newtons. And those are derived quantities, both derived quantities and derived units, no matter how you look at them. So as an overview and perspective, and I want us to get used to this, is that formulas are not an end of them into themselves. They represent ideas and the understanding of ideas. On the AP equation sheet, which all of you probably have already, of all the formulas I just listed above, these are the only ones that are present on the AP Physics equation sheet. Notice, it consists of these two and this one. This isn't one that we ever really even need to use. And these two are relationships. So that means the AP equation sheet omits all definitions. And of course, definitions are things that we want to know. So that is an overview. And over the coming days, there will be an installment or lesson on each and every one of these formulas, what they mean, how to use them, and interpret them. Thanks for watching Physics in a Flash.